Exploring the entropy catastrophe, gold's superheated stability. In a groundbreaking study, researchers have pushed gold to temperatures 14 times higher than its melting point without causing it to liquefy, challenging conventional thermodynamic limits and shedding new light on the extreme stability of materials. This discovery, published in Nature, was made possible through the use of ultrafast laser heating and high-resolution inelastic X-ray scattering techniques, allowing scientists to explore the previously unattainable entropy catastrophe threshold. The entropy catastrophe is a critical point where the entropy of superheated crystals equals that of their liquid counterparts. Until now, this phenomenon has been impossible to investigate experimentally due to various instability events occurring at lower temperatures. However, by employing ultrafast laser heating and high-resolution inelastic X-ray scattering, the research team has been able to delve deeper than ever before, revealing that gold maintains its crystalline structure even at temperatures approaching 19,000 K, far exceeding the metal's standard melting point. But here's where it gets controversial. The team's findings challenge the long-held belief that a solid becomes thermodynamically unstable once it reaches about 3 times its melting point. Advances in short-pulse laser technology have enabled heating rates exceeding 10 to the power of 14 K per second, bypassing the slower destabilizing processes that typically lead to melting. Previous experiments had superheated gold to between 1.4 and 2.1 times its melting point, which theoretical models suggested was near the limit. However, this study directly measured ion velocity distributions using inelastic X-ray scattering, offering a model-independent method to access lattice temperatures, a significant improvement over earlier work that relied on indirect methods to estimate ion temperatures. And this is the part most people miss. The researchers found that gold films, just 50 nanometers thick, retained their crystalline structure for more than 2 picoseconds when irradiated with ultrafast laser pulses, achieving heating rates above 10 to the power of 15 Kelvin per second. At the highest heating rate of 6 times 10 to the power of 15 Kelvin per second, the temperature peaked at 19,000 plus or minus 4,000 Kelvin, approximately 14 times the metal's melting point. In both cases, the samples remained crystalline for far longer than the time typically required for melting to occur. The researchers monitored the lattice structure of the gold films using wide-angle X-ray diffraction, observing the presence of 200 and 111 Debye-Scherer rings, which indicated long-range order. These peaks gradually decayed as atoms vibrated more intensely, with the 200 peak fading faster than the 111. Surprisingly, neither peak disappeared within the 3 picosecond observation window, indicating that the material had not melted. Moreover, the Bragg peak positions remained fixed, suggesting no significant expansion or ablation, which contradicts expectations from entropy models, predicting rapid breakdown once the entropy of the solid phase exceeds that of the liquid. The team used a multi-photon expansion approach to precisely model the scattering during heating, fitting Voigt profiles to experimental data via maximum likelihood estimation. Electron thermal properties were also modeled to confirm uniform heating under experimental conditions. Electron thermal conductivity was estimated to be between 3,000 and 5,000 watts per kilogram, and heat capacity around 0.3 to 0.5 joules per gram Q, leading to a thermal diffusion time across the 50 nanometer sample of about 0.5 picoseconds. These conditions supported the assumption of near-instantaneous uniform electron heating across the sample. Laser fluence was adjusted using an iris before the final focusing optics, allowing the researchers to control and isolate energy delivery. Only scattered X-ray photons corresponding to known fluence bands were included in the temperature analysis. Temperature and structural measurements were taken simultaneously using Diopta software to process X-ray diffraction patterns. The study's most striking result is that the system avoided the long-assumed entropy crossover point, where the solid's entropy overtakes the liquid's. This threshold has long been considered a thermodynamic ceiling for solids under heat. But by heating fast enough to suppress expansion, the researchers showed that gold can remain stable well beyond this point. The entropy of the solid phase stayed below that of the liquid at all temperatures achieved, suggesting that the entropy catastrophe may not be a true upper bound, at least not under ultra-fast heating conditions. Because the heat capacity of the solid under these extremes is governed by universal constants, and the liquid phase is still poorly characterized, the point at which entropy curves cross remains uncertain. Deviations in heat capacity for non-equilibrium systems and thin films may also shift the entropy balance. The implications of these findings extend beyond gold. Understanding material stability under ultra-fast, high-energy conditions could inform the design of more resilient materials for extreme environments, such as those encountered in nuclear fusion, astrophysical research, or ultra-fast electronics. The study challenges the conventional wisdom that there is a hard limit for superheating, suggesting that if the heating is fast enough, the predicted limit can be exceeded by a wide margin. It may not exist at all. The crystalline structure of gold withstood temperatures that conventional thermodynamics say should be impossible for a solid. This discovery opens up new possibilities for material science and could lead to the development of materials capable of withstanding extreme conditions previously thought to be impossible. Gold heated to 14 times its melting point without melting. Mind-bending science. In a groundbreaking experiment, scientists have used ultra-fast, high-intensity lasers to heat gold to an incredible 14 times its normal melting point, without the metal turning into a liquid. This feat, which was detailed in a study published in the journal Nature, has smashed decades-old theories about the stability of solids and provided the first reliable method to precisely measure the temperature of extremely hot systems. But here's where it gets really interesting. The solid gold sample reached a mind-boggling 19,000 kelvins, 33,700 degrees Fahrenheit, or 18,700 degrees Celsius, a temperature that's 14 times higher than gold's standard melting point of 1,337 kelvins, 1,947 Fahrenheit, or 1,064 Celsius. And this is the part most people miss. Normally, solids and liquids have a defined temperature at which they change from one state to another. But under certain conditions, materials can be heated beyond these limits without changing state, a phenomenon known as superheating. In the 1980s, physicists calculated the limit of the superheating effect for solids as 3 times the melting point, which they dubbed the entropy catastrophe. So, how did the gold sample remain solid at 14 times its melting point? The team suggested that the sheer speed at which they heated the gold prevented the crystal structure from expanding during the timescale of the experiment. It's important to clarify that we did not violate the second law of thermodynamics, said Thomas White, an associate professor of physics at the University of Nevada, Reno. What we demonstrated is that these catastrophes can be avoided if materials are heated extremely quickly. In our case, within trillionths of a second. But here's a controversial question for you. Could this experiment pave the way for new materials with unprecedented properties? Or is this just a scientific curiosity with no practical applications? Let us know what you think in the comments. Gold's surprising behavior when superheated beyond melting point. Imagine heating gold to temperatures so extreme that it defies conventional wisdom about melting points. A groundbreaking study has done just that, revealing that gold can remain solid far beyond what scientists previously thought possible. This discovery could revolutionize our understanding of how matter behaves under extreme conditions. The international team of researchers behind this study used ultra-short, high-intensity laser pulses to push thin gold fragments past a critical threshold known as the entropy catastrophe. This is the point where a solid is theoretically too hot to stay solid. Think of it like a melting point, but for scenarios where the rules of physics get a bit wonky. Here's where it gets fascinating. In a process called superheating, A solid can be heated so rapidly that its atoms don't have time to transition into a liquid state. This means crystals can stay intact well beyond their usual melting point, albeit for an incredibly brief period. But here's where it gets controversial. The researchers found that gold could be heated to 14 times its standard melting point before it finally liquefied. Typically, the entropy catastrophe is thought to occur at just 3 times the melting point. Using a novel method to measure absorbed heat energy, the team discovered that gold could withstand temperatures up to 19,000 Kelvin, around 18,700 degrees Celsius, or just over 33,700 degrees Fahrenheit, and remain solid for more than 2 picoseconds. That's a trillionth of a second. This might sound like it defies the laws of thermodynamics, but it doesn't.